going to keep talking about angular momentums, and then we'll move on to spin. And explicitly, we're going to derive the spectrum of the angular momentum operators and their coordinate representations. Right. So from last time, the most important result we got was by considering the rotation of a system, we derived these commutation relations. So and these ijk could be x, y, and z. And then this epsilon ijk gives their cyclic order. So starting from here, we're going to derive everything we can about angular momentum. So first, I'm going to define two operators. L plus, and this is given by Lx plus I Ly, and then L minus, which is Lx minus I Ly. So you notice that, first of all, they are Hermitian adjoints of each other, right? Because all of these operators are self-adjoint. And now, let's think about an interesting observation is how Lz commutes with L plus or L minus. Right? Since L plus is a linear combination of Lx and Ly, we can compute this commutator with knowledge of how Lz commutes with Lx and Ly. Don't write it down explicitly. Lz, and this is Lx plus I Ly. And this commutator is additive. Right? So we can write Lz Lx plus I times Lz Ly. Okay. Remember, whichever factor is attached to one of them is actually attached to both of them because the commutator is a product at difference. Okay, so Lz and Lx, z and x are in the correct cyclic order, so they commute to give you IH bar Ly, right? Lz and Ly are in the wrong cyclic order, so they commute to give you minus IH bar Lx, right? And then in the end, you'll get, if we take out a H bar, right, I Ly, and then I minus I is 1. And this is Lx, so Lx plus I Ly, this is just L plus. So Lz commutes with L plus in this manner, all right? And from this equation, we can directly write down the commutator of Lz and L minus. How do we do that? Since we know that L plus and L minus are Hermitian adjoints, we can take the adjoint of this commutator. This is correct. How do you take the adjoint of a commutator? You just exchange their order, right? And then you write the adjoints of each of them. Because the commutator is a product. So this is L minus Lz. And then if we write this in the normal order, placing Lz in the front, we're going to add a minus sign. So Lz commutes with L minus in this manner. Okay, and today we're going to make extensive use of these two commutation relations. So let me write it over here. Okay. The commutator of Lz with L plus or minus is equal to plus minus H bar L plus minus. Okay. So, and by the way, these are called raising and lowering operators, and you'll see why in a second. In your homework, I asked you to, we defined a total angular momentum operator of, given by L squared is Lz, Lx squared plus Ly squared plus Lz squared. And I wanted you to check that L squared and Lz commutes. Now what does it mean when they commute? It means that there exists, they have simultaneous eigenfunctions, right? But without checking, we actually already showed that in the last lecture. When we solved the spherically symmetric problem in spherical coordinates, we found that there was a simultaneous eigenfunction of rotation, the rotation in z direction and the total rotation. So it's reasonable to say that Lz commutes with L squared. Okay. but you will show this explicitly in the homework. Okay. So let me write this here. And since there's nothing special about the z direction, we say that L squared will commute with any of its components. So it is possible, based on these, let me write, instead of LZ here, let me write Li. So based on this commutation relation and this here, we deduce that it's possible to know the total angular momentum of a particle and one component of it. But because the different components not commute, you can only know one component of it, but not two. Okay? Alright. So now let me use this L plus and L minus operators and construct an identity we'll use later. So what is L plus, L minus? So this is Lx plus I, Ly, Lx minus I, Ly. Okay. So you get Lx squared, and then the I minus I gives you Ly squared, and then you get plus I, Ly, Lx minus I, Lx, Ly. Now this is just I times the commutator of Ly and Lx, which is minus I h bar Lz, right? So this is Lx squared plus Ly squared plus I times minus I h bar Lz. And now let me use this definition here to write Lx and Ly in terms of L squared and Lz, because these are the two operators we're going to work with. So this is just L squared minus Lz squared, and then this is plus h bar Lz, correct? Okay. So this is L. And if we did L minus, L plus, everything is the same except that over here we would have these two factors in different order, right? So instead of Lz, we get a minus Lz, the commutator. Instead of, we get a commutator of Lx and Ly, right? Which is I times that would be minus Lz. So L minus, L plus is. So these two, we will also make heavy use of them. Right, so let me go ahead and copy them down over here. And these are the formulas that you should remember for angular momentum. They allow you to solve any basic problem with angular momentum. So it pays to memorize them, actually. Okay, so now let's think about, we said that since Lz and L squared commute, it's possible to construct a eigenket, a simultaneous eigenket of L squared and Lz, right? And let's label the eigenket with the respective eigenvalues. So since we don't know beforehand what the eigenvalues are going to be, I'm going to use L squared and Lz without the hat to label their eigenvalue. Okay. So the simultaneous eigenket, and we start from here. The simultaneous eigenket looks like this: L squared and Lz. Okay. They're defined by two eigenvalues, and you can get a simultaneous eigenket because they commute. And the action of L squared, and remember this is the operator, is equal to picking out the eigenvalue L squared. And then the action of Lz is just picking out the eigenvalue Lz.
Does anybody have any problem with that notation? L squared, Lz notation?
Is that okay?
Any problem?
I can call them anything you like. Because right now we, yeah.
Just as a reminder, so since they commute, then they share the same base of orthogonal.
It's possible to find a shared orthogonal basis.
Okay, and that's why you write
Yeah.
with
Yeah.
them combined.
Yeah.
Okay.
I could also use alpha or beta or whatever. It doesn't matter here. Okay.
So maybe you can actually define what the implication is, L squared LZ, when you say something like that, what does it mean?
It means that this ket is characterized by being the simultaneous eigenket of two operators, L squared and LZ, and the respective eigenvalues are L squared and LZ. Okay. Does this get confusing, or should I maybe?
If it's not confused, if students are confused, then you should explain.
Maybe I should. If not, then I'll use it. Otherwise, I can use alpha or beta. Yeah. Everybody is okay with this? I guess. All right. So from the second eigenvalue definition here, we can write down, of course, that LZ squared is equal to LZ squared. Right? So LZ squared. Remember, whenever you don't see the half, then that's the eigenvalue. So if you remember that, there should be no confusion. Okay. So now let's think about what is L squared minus LZ squared. What is the expectation value of this? Taken with respect to a simultaneous eigenket. So we can write this as, obviously this is just L squared minus LZ squared, right? Because these are just eigenvalues, right? Now, but we can use this definition here to turn this into Lx squared plus Ly squared. Both of these are Hermitian operators, so their eigenspectrum are real, so the square of their eigenspectrum are positive, right? So this thing is strictly greater or equal to 0. But since Lx and Ly don't commute, you know that it cannot be 0. But let's just say that.
So there's no hat on the second one. LZ hat and no
Oh,
hat.
sorry. So we can deduce that because these are non-negative, right? This must be greater than or equal to 0. Right? So the requirement that the rotation in the z direction does not exceed the total amount of rotation is automatically satisfied in our operators. We didn't have to impose that as a separate requirement. This is already built in to these definitions. Okay. And the only thing we require is basically these commutation relations and the fact that they are Hermitian. Okay. Right. So based on this, we know that LZ must be bounded by L squared. Right. Now let's look at the what are the actions of the raising and lowering operators, and why do we call them that? We start with the eigenkets of LZ, and we consider the action of the raising operator on it. And let's take it, afterwards, let's look at its LZ eigenvalue. Okay. So we construct something like this. But we know the commutator of LZ and L plus, so I can go ahead and take LZ across, right? I take LZ across by writing a commutator, right? So this is equal to correct? But
So
now,
how do you get that? You have to go to detail on how you go from the left hand side.
Oh,
to the
sorry,
right hand
sorry.
side. How do you go?
I forgot the commutator is written here, and they commute with the rest being h bar L plus. So I forgot to write that H bar L plus here. Now it should be correct. Okay. So now LZ sees an eigencat, picks out the eigenvalue, and the eigenvalue we're free to move around because it's a number. Correct? So this just gives you LZ plus H bar. Right? So now it tells us that if I view this as a whole, a new cat, and this as a new cat, it says that this cat is an eigencat of LZ with the eigenvalue LZ plus H bar. Right? So this tells us two things. First of all, well, the action of the, if I start with a LZ eigencat, right, the action of the raising operator is going to take it into another LZ eigencat. Another thing is that the eigenvalues of LZ are separated by integer multiples of H bar. So based on the commutation relation, we already get that the spectrum of the angular momentum operators are quantized. Quantized in the sense that they must differ by integer values, integer multiples of H bar. Right? Okay.
Do you switch the order between the first line and the second, for the left?
This and this. For
The
this one.
L plus LZ becoming LZ L plus.
Oh,
It's just an eigenvalue.
it's an eigenvalue, so I'm free to move it around. Okay. So now the action of the raising operator is to raise the eigenvalue of LZ by H bar. So we can write, it must be true that if I apply the raising operator onto a LZ eigencat, the result must be proportional to a new LZ eigencat with the eigenvalue LZ plus H bar. But I only say proportional because we don't know what the proportionality constant is, and later we'll find this. But right now, based on this observation and this observation, there must be a maximum value of LZ such that if I raise it any further, I'm going to get 0 because the spectrum of LZ must be bounded by the total angular momentum. Right? Similarly, if I apply the L minus here, and you can carry out the algebra, I'm going to get LZ minus H bar because they commute with a minus H bar L minus here, right? Okay. So we get that for some maximum value of LZ, I can write L plus, and let's say LZ max. You can raise it no further because it is bounded by the total angular momentum. So we must have, for some, and we'll go ahead and look for this, the maximum value of LZ. Similarly, for L minus, you will have some minimum value of LZ such that you can lower it no further, right? So to find that, well, it's easy because previously we have computed these products, and we're going to use them to find what are the maximum and the minimum values. So I start from here, from 1. Now let's compute. I take this to be a cat, and let's compute the bra. So if I compute the bra, that's what it is. You take the Hermitian adjoint of the whole thing, right? So this becomes the bra, and then the operator goes to its Hermitian adjoint, and it operates from the right. Right? Okay. So this is just the bra of this, and we know that this is also 0. Okay? Because if I take the Hermitian adjoint of 0, it's still 0. And then let's take the inner product of this bra with itself, so with the cat. on the right hand side, this gives you 0, because both of them are 0. Is everybody okay with this? I'm not using this. Okay. I'm starting from 1, taking the bra, and then computing the, basically computing the norm of this thing. Okay. And the norm is just 0, because it itself is 0. Let's replace L plus, L minus L plus with what we have, the product form we have written out over there. I mean the sum form. L squared LZ max. And this is L squared minus LZ squared minus H bar LZ. So the advantage of writing it in this form is now having turned the product of L minus and L plus in terms of L squared LZ squared, and operating on these eigencats of L squared and LZ, we can just compute this. We can compute the numerical value of this. And this turns out to be L squared minus LZ max squared minus H bar LZ max. This is equal to 0, right? Okay, so this is what we get from computing the norm of 1. Now if we compute the norm of 2, we're going to get L plus L minus, right? So L plus L minus is going to give you L squared minus LZ squared plus H bar LZ. So we get that L squared minus LZ, but now the eigenvalue is the minimum, right? Plus H bar LZ minimum is equal to 0. So the second one gives you this, right? Right. So now let me compute the difference, 2 minus 1. This side is still 0, right? L squared now cancels, and we're left with, what's over here? LZ max squared minus LZ minimum squared. And then, since it's this plus this, it's plus H bar LZ minimum minus LZ max. This is equal to 0, right? So now I use the formula everybody knows. LZ max plus LZ minimum times LZ max minus LZ minimum, right? And then it's plus H bar, I use minus H bar LZ max minus LZ minimum is equal to 0. So I can combine them into LZ max minus LZ minimum times LZ max plus LZ minimum minus H bar. Yeah, I must have made a mistake somewhere. Okay. L minus L plus.
L is plus.
Well, where is plus?
2 minus 1 gives you H bar times L Z minus plus L Z max.
Yeah, that's right. That's right. Yeah. So yeah, this makes sense. Yeah. Correct? From up to this line. Right. So now, since the maximum value minus the minimum, and this should be plus H bar, right? Let me see. Plus H bar. Okay. So since the maximum value minus the minimum value, this thing is strictly positive, right? And then plus H bar, this factor here is positive, right? And since the product is 0, we deduce that we must have LZ maximum is equal to minus of LZ minimum, right? Okay, this is one requirement for based on the norm of these being 0. Okay. Another requirement is that since we showed by applying this the action of the raising operator is to raise the eigenvalue of LZ by an integer multiple of h bar, right? So it must be that if I started with the LZ minimum eigencat of LZ, then if I raise it by an integer steps, I must be able to reach LZ max. Right? So LZ max and LZ minimum, they differ by integer multiples of h bar. Right? So I must be able to write LZ max minus LZ minimum is equal to some integer, and let's call this integer n times h bar. Right? This is the action of the raising operator. Right? So what does these two mean together? N or right, they're either, so this tells you that 2 times LZ max is equal to an integer multiple of h bar, right? So it tells you that the LZ max and LZ minimum, they're either integers or half integers, right? Okay. So again, we have reached this quantization condition. Remember, when we considered the eigenvalue problem explicitly, what did we do? We require that either the eigenfunction itself, either the wave function itself, is invariant under 2 pi rotation, or that a superposition and the magnitude squared of a superposition of the eigenfunction remain invariant under 2 pi rotation. So you get the same result, the same kind of
You
function.
see how you get the second line again, LC max minus LC min is to the n h bar.
Okay. Because we know that all of the eigencats of LZ are linked by this raising operator. So if I am able to order them from top to bottom, then I can go from the bottom by successively applying L plus, I can reach the top. And the LZ minimum and the LZ max are just the bottom and the top, right? And since the action of one action and the action of applying one raising operator is to raise it by 1 h bar. It must be that going from bottom to top, I raise it by an integer multiple of h bar. Okay? So these are spaced by integer multiples of h bar. Okay. Now really, remember when we did the explicit problem, the requirement that LZ max is equal to minus LZ minimum. What was this requirement? It was a requirement that there's nothing special about the positive z direction. It can just as well be rotating in the minus z direction, right? So you can see that the symmetry of top and bottom is also built in here. Okay? So you remember everything is derived from the commutation relations and assuming that they are Hermitian operators. Okay. So now, from here, we also get what is the value of L squared in terms of LZ max or LZ minimum. Right? So we get that L squared going from here. L squared is equal to LZ max times LZ max plus H plus. Right? Now let's reduce our notation. And we'll use what's conventional. We'll use L to denote the eigenvalue related to L squared. And because it's not exactly a square, right? This is something plus, times something plus 1 if I take out the h bar. Right? So I would like the eigenvalue to be dimensionless, first of all. So let me write L squared is equal to L times L plus 1 times h bar squared. This is to get the dimension correct. So you take 1 h bar L from here. And remember LZ max, the LZ has dimension of h bar, right? And then you take 1 h bar from here, and then you get the h bar squared. So by this convention, we're saying that the LZ max is L, right? And what are the possible values of L? There are integers or half integers. Right? And then for the LZ, I'm going to use M. Okay. So then our definition here of L squared and LZ turns into, we can label the eigencat with L and M. Right? So the eigencats goes to L and M. This being representing the total angular momentum, and this representing the Z projection of it. So if I operate L squared on this, I get L times L plus 1. And remember the unit. All right. And then if I operate on this with LZ, I get L H bar M. Okay. So now we have found the simultaneous eigencats of L squared and LZ operators. I remember when we did the explicit problem in the spherical coordinates, for the for the theta direction, we used the eigenvalue L times L plus 1, right? And it turns out that the eigenvalue problem is factorizable. So, and the reason is actually here. Okay. So now, if we go back to this inequality here, L squared is greater or equal to LZ squared. We deduce from here that actually L squared must be strictly greater than LZ squared, because the maximum value of LZ is just L. Right? The maximum value of M is just L. Right? Since L plus 1, this is strictly greater than L squared, we get that the L squared is strictly greater than LZ squared. And what is the reason for this? Well, previously I said that since the sum of the square of two non-commuting operators, Hermitian operators, not only is this positive, non-negative, this is actually strictly positive because I cannot make them both 0 since they don't commute. Right? This is that statement exactly. Okay. So the total angular momentum is always greater than the Z component, the Z projection of it. And this is to allow some uncertainty in the X and Y direction. Alright? Is everybody okay with this?
Did you get L squared there and down there you have M? I don't follow that.
No, I'm just relabeling. So I'm saying that previously we used the LZ to denote the eigenvalue of the LZ operator. Now it's used M because everybody used M.
So why do we have L squared there? How does that relate to that?
Oh, okay. So the maximum value of LZ, I'm comparing the maximum here. The maximum value of LZ is just L, right? So the maximum value of M is just L. Okay. So maybe I should write minus L, this over here. That makes it clear. All right, so the uncertainty relation and all that are all built into the commutation relations. And one can deduce everything about angular momentum based on those commutation relations. All right, so now we move on to the next topic. And that is, we said that that is the actual spectrum, including how things are scaled. So now let's turn and solve this problem. We said that the raising operator takes a eigencat and turns it into the direction of another eigencat. And now let's find this proportionality factor here. Okay. These things are important. Are there any questions? No? And remember that everything we work here applies to the spin as well, because we haven't made the distinction between angular momentum and spin yet. So let's write that problem in terms of our new notation. We have L plus operating on a eigenket Lm. This is equal to, let's say, some proportionality constant that is a function that is labeled by L and M. And this takes it into, well, let me take the L plus must have the unit of H bar, right? So let's write the H bar out so that everything else is dimensionless. L M plus 1. Right? Okay. Right. So now what do we do with this? The same thing. Let's take this and compute the graph, right? Which is L M L minus, right? This is equal to L M plus 1 H bar. There's a conjugate here, right? Now, by imposing the normalization condition, if I take the norm of this cat, it should be 1. Right? If I take the norm of this cat, and that is saying that H bar squared L M plus 1 C L M squared M plus 1. This is equal to L M and normalization condition requires this to be 1, right? Okay. So this is simple, right? This side, since these two are the same, this is just H bar squared C L M squared. Okay. And then over here, what is this? We again use the turning the product form into sum. So this is L M L squared minus LC squared minus H bar LC L M. This is equal to 1. And then we pick out the eigenvalue.
Square in the second term.